Jai Hind everyone. Dear students, today we are going to start a new topic in computer organization and architecture, and today's topic is mapping function in cache. So, I am Professor Dr. Akhilesh Verma from Department of Computer Science and Engineering, Akgec Engineering College, Ghaziabad. So, let's start the topic mapping function. Now, mapping function determine how many blocks are placed in the cache. So, the memory unit is divided into memory blocks. So, if we see this diagram, here we can see there are 4096 blocks starting from block 0 to block 4096, fine, and each block is composed of 16 words. So, these blocks in the main memory we can see is placed here, and it has to be brought into the cache which has limited space for the blocks. So, we can see there are total 128 blocks here that can be placed here, and they are from block 0 to block 127. So, if we see the statistics of example here, we can see that in a simple processor with cache and main memory, cache consists of 128 blocks and each block is consisting of 16 words. So, what does it mean? It means that the block here is composed of 16 words. So, every block is having 16 words, fine. Now, since the total size of cache is 2048 or 2k words, so we can easily find out how many blocks can be occupied in the cache just by dividing the 2048 divided by the 16. So, it will comes out to be total 128 blocks here, okay. So, it will be 128 blocks here, fine. If we see the size of memory, we can identify using the bit used in address. So, the memory is addressed by 16 bit. So, the size of memory is 64k, that is 2 raised to power 16 addresses are available to be addressed in the main memory. Similarly, since we know that the word size, the block size is 16 words, so we can identify from this 64k words memory how many blocks are there. So, we can divide 64k words with 16k words. So, we will get the total number of main memory block is equals to 4k, that is 4096, right. So, this is a very important thing that we need to understand before we start understanding the mapping process. So, we come to the first mapping technique, that is called as direct mapping, and we already know that the memory has 4096 blocks and the cache has space for 128 blocks. Depending upon the requirement, if any particular word can be addressed by a processor within a main memory. So, if any particular word is accessed from a block, it will be somewhere inside the block, fine. So, the word within a block is identified by the 4-bit, that is called as word address, and that can be identified using 4 bits. So, this least significant 4 bits LSBs are used to identify the words within the 4 bits. So, when an address is generated, physical address is generated, okay, physical address is generated, the bits used to address is 16 bits. We can see that the least significant 4 bits, that is called as the word address, is used to identify the particular word within a block, fine. So, whenever a block a particular word is requested within a block, we need to bring that block into the cache memory. So, where I will bring that cache memory block is called as mapping. Fine. So, out of these 128 locations of blocks that can be stored from the main memory, which particular block is to go. So, that decision is taken by the mapping technique, and the first technique is called as direct mapping technique. So, how direct mapping technique works? So, out of these blocks, assume that there is a block J of main memory that has to be mapped into the main memory. So, direct memory works on a modulo operation. So, J modulo 128. Okay. So, certainly 0 will be mapped at 0 because 0 modulo 128 is 0. Similarly, if we see 129, so 129 modulo 128 will be 1. So, we can see here, that this block 0 will be mapped here, fine. And similarly, if we see block 1, it will be mapped to block 1, and 128th block will be mapped here. Now, what will be the block 129? Okay, so it will be mapped to which location? It will be mapped to location this one, fine. So, what will happen? Sorry, this one block 1, because 129 modulo 128 1, and block 128 will be mapped here, fine. So, in this way each and every block is mapped to the main memory, to the cache memory block. So, block 0 is mapped to block 0 of cache, block 1 is mapped to block 1 of cache. Similarly, 128 is mapped 120 is mapped here, and 129 is mapped here, likewise. So, every block is mapped directly into a particular cache block. So, what will happen? More than one memory block is mapped onto the same position in the cache. So, you can see here that block 0, okay, in the cache, or you can say cache line 0 is mapped with block 0 as well as block 128. So, there are 2 blocks mapped here, we can see, but how many blocks are mapped here? So, we can see there are 32 blocks, okay, 32 blocks are currently mapped in one cache line. So, there are 32 blocks mapped in a particular one cache line, fine. So, what will happen? May lead to contention, means that multiple blocks are mapped in the same cache line, fine. So, if cache is not full, other cache blocks are available free, but since they are mapped to the same location, 32 main memory blocks are mapped to the same location. So, what will happen? There will be contention, okay, space is available and you are not able to utilize it. So, to resolve the contention, we need to replace the old block, leading to trivial replacement, means we have to remove the existing block even though it is being used. So, there is a one problem that is very important in the direct memory mapping, is that we have to remove the existing block if some new block has to be brought to the same memory, same block where the main memory block is mapped, okay. So, this memory address is divided into 3 fields, 16 bits. The first 4 bits, that is least significant bit, is determining the word within a block, okay. So, whenever a new block is brought into cache, okay, where it will go? So, we already know that we have said that modulo operation is there. So, next 7 bit is the address at where the particular word will go. So, 2 raised to 7 is equals to 128, okay, fine. So, this is the cache line 1 and this is the cache line 128. So, block 0 will come here and block 128 will come here, because that address is determined by the block bits in a address of 16 bits. Fine. So, next 7 bit determine which cache block this block will placed in. Higher order 5 bits determine which of the possible 32 blocks are currently present in the cache. So, we already know that 32 blocks are mapped into the same cache line. So, which particular block is present here? It is determined by these 5 tag bits, and the tag of that particular block is present in the cache for later on searching. So, this will identify out of 32 which particular block is present here in the main memory. So, whenever a particular memory address is generated, okay, and it is first checked with this tag value whether it is present in the cache memory using this tag. Fine. So, what is the problem here? The one of the important problem here is that many blocks are mapped to the same location, okay, then there will be a replacement to be done of some trivial way, okay, that will hamper the problem. And also one problem is that the tag is meant to search a particular block present in the cache, okay. So, we have to search a 5 bit tag simultaneously in the cache for the identification of the block present in the cache. Now, another approach, or you can say another extreme approach. So, this is the one end of the scheme. So, there is other end of the scheme, okay, and these are two extremes of mapping. So, one end is direct and the second end is associative mapping. Here what is thought that why we will reserve a particular block to map only 32 cache memory blocks. Why not put any of the block in any of the location of the cache line. So, whenever a request comes for any word, it will go to the free available next block, okay, and so on until unless all the blocks are free. Fine. So, this way of mapping is called associative mapping, means that all 4096 blocks of main memory are associated with this particular cache and they can go anywhere. So, what will happen? We can see that it can occupy maximum 128 blocks. Fine. So, if we see, if we bring any of the block here, so what will happen? We have a freedom to place anywhere. So, what will happen? The memory address can be divided into two fields. One is low order 4 bits to identify word within the block, okay, and when this particular block is brought here, it will have a tag. The higher order 12 bits identify the memory block when it is resident in the cache. So, if we see 2 raised to power, okay, 12, fine. How much it will be? It will be you can say 2 raised to power 10 into 2 raised to power 2. So, it is 10024 into 4. So, you can see there are 4k tags possible here. Interestingly, if you see here, how many blocks are there? We can see that for every block we can have one tag. So, each and every block in the main memory has their own separate tag. So, whenever we bring any particular block in the associative mapping anywhere, each block will have their own tag. Okay. So, instead of having a direct mapping as previously done, we will bring block and put anywhere, and each of the block present in the main memory in the cache memory, sorry, have their own tag, and we can search that using this 12 bit tag. So what is the advantage here? The advantage is here is that instead of trivial replacement, we have a possibility to store on the freely available cache line in the cache memory, and until unless all the 128 is not occupied, we are having the space available in the cache, and when we have all 128 filled, then we have to replace the block. So it is flexible and uses cache efficiently. So replacement algorithm can be used when replacement of existing block is required in case of cache memory is full. Fine. So at what cost? We have created an extra 12-bit tag, that is the tag size is increased. So it will cost higher with respect to direct mapping, because we have to search 128 patterns in the cache memory for identification. So the cost of associative mapping is more than the direct mapping. So you can easily identify and see this, that direct mapping, okay, and associative mapping, there are two extreme ends. So direct mapping is simple, but it is having a trivial replacement. So there is a performance loss, but here it is complex, because tag size is 12-bit, okay, and here it is simple because tag size is 5-bit. So the hardware is simple in the direct memory, so cost of direct memory is less with respect to associative memory, where the tag size is 12-bit. So the cost of associative memory is high, because we have to search 12 tags. So dear students, can you think some intermediate solution? Yes, there is an intermediate solution, that is called a set associative mapping, which brings the best part from direct mapping as well as from the associative mapping and merge it into a single technique. So you can say set associative is a some in between technique between direct mapping and associative mapping. Okay, direct mappings is also taken care, and as well as associative mapping is also taken care. So what they have done, they have grouped the block of cache depending upon the set size. So now this is a set of 2 blocks. So this is another set of 2 blocks. Likewise, there will be another set. So out of 128 blocks present in the cache memory, if we divide it by 2, okay, so total 64 sets are available here. So set 0, set 1, and this is set 63, total 64 sets are there. So basically cache memory is divided into smaller sub sets, and they act as a associative mapping, and this individual set is mapped as directly. So if you see the address scheme here, to identify a particular address, so the word length required to identify a particular word in a block is used by the 4-bit, that's fine, but the next 6-bit is identifying which particular set a particular block is mapped. So we can see there 2 raised to power 6, okay, so it is 64. So 64 sets are there, fine. So each block is mapped directly to a set, okay. So any block cannot be mapped in other set, so the set is fixed. So we can say that the bringing any block to a cache memory and bringing to a particular set is a directly mapped. So bringing to a set is a direct mapping. Now within the set there are 2 choices. First choice is whether it will go at this location or it will go at this location, both are free. So where it will go? So, we can have a choice to bring at either first location or second location depending upon which one is free. So, within the set we are having a associative mapping. So, basically set associative is having the benefits of both direct as well as associative. So, set is mapped directly, there is no option to change the set, and within the set there is a two option whether we can go to block 0 and block 1. Now, dear students, say for example, if there is a set, okay, and it has a 4 blocks, block 0, block 1, block 2 and block 3, 4 blocks within a set. So, that particular set is called as 4-way set associative, and this particular mapping approach is called as 2-way set associative, because there are 2 ways to move within the set. So, if you have 4 blocks within a set, there are 4 ways to move within a set. So, within a set there is associative mapping, and when you are going choosing a set, it is a direct mapping. Fine. So, we got a freedom of direct mapping as well as the associative mapping for the cache management. So, block of cache are grouped as set. So, what will happen? We have direct mapping within the set. Mapping function allows block of main memory to reside in any of the specific set, that is a direct. Fine. And divide cache into 64 sets with 2 blocks per set. So, memory block 0 to 64 and 128 map to block 0, and they can occupy either of the 2 positions. So, that is the associative mapping. So, memory address is divided into 3 fields. First field is 4-bit address and 6-bit determines the set number that we have seen here. Okay. And higher order 6 bits are compared to the tag fields of the 2 blocks in a set. Okay. So, these set has 2 tags. So, total 128 tags are available in the cache memory block. So, this 6-bit tag will be used to search the tags present in the cache memory. So, the set associative mapping is a combination of direct and associative mapping. So, what will happen? The number of blocks per set is design parameter for a cache performance. So, depending upon the requirement, we can choose what performance we require. So, this is a critical parameter. So, one extreme is to have all blocks in one set, okay, requiring no set bits, fully associative. Fine. So, we are removing this, and 6 plus 6 is 12. Fine. And other extreme is to have one block per set, the same as direct mapping. Fine. So, we have this one, word, block and tag. Fine. So, even though we choose out of these 3, direct, associative and set associative, another important thing is that in each of these 3 cases, if the availability of cache is not there in a particular set or in a particular directly mapped mapping approach or set associative, what you will do? So, there is need to replace the block, and the memory block occupied in cache is fixed. So, there is a need of replacement strategy to be incorporated. So, associative and set associative provide some flexibility in deciding which memory block occupies which cache block. Fine. So, there is a very rare chance for replacement. So, when a new block is to be transferred to the cache and all positions it may occupy are full, which block cache should be replaced? So, certainly the locality of reference suggests that it may be okay to replace a block that has gone the longest time without being replaced. Okay. So, there is a policy that is called as least recently used block strategy called LRU replacement algorithm, and it is extremely used in this technique because we are not using it. So, we were replacing. It provides a poor performance in some cases. Basically, performance of LRU algorithm may be improved by introducing a small amount of randomness in which block might be replaced. So, some cases are there where the least recently used algorithm may cause a problem, because it will be like program behavior dependent thing. So, we are bringing it out by the algorithmic change. So, another way is to use the oldest block, but however the LRU or the oldest block has there is extreme analysis to be done to choose which particular replacement algorithm, or LRU or FIFO. So, dear students, today we have learned the mapping technique, and also in case we are doing mapping, we do require a replacement, and then in case of replacement we have two approaches. One is that we use a least recently used block replacement algorithm or the oldest block replacement algorithm, and both have their own advantage and disadvantage. Thank you and Jai Hind.